Greetings once again, chematures. Let's play on words. Chemature, amateurs, chematures. So this lesson here, this is to take a quick look at something that we call periodic trends. Each of these trends or patterns relates to valence electrons on atoms. So we have three different trends that we can look at as we move down a group or across a period on the periodic table. What happens to the ionization energy, the electronegativity, the electron affinity. The beauty of this is remembering them is identical. Let's jump right in. So we have this thing called ionization energy. Really what this is, it's energy required to remove electrons from an atom. What's going to determine how much energy we need is how well attracted those valence electrons are. When they're well attracted, it takes more energy to remove. So large atoms, when the distance is rather large, we end up with a weak attraction. They're easier to remove. Small atoms, they're harder to remove. It requires more energy. So what we can think about is the lowest ionization energy would be the largest of atoms down near the bottom. The highest would be in the top right corner, but we have to exclude the noble gases. The reason being the noble gases already have octet, and they tend not to interact or react, so they don't have to lose electrons or gain electrons. They're relatively stable in their atom form. So we say metals have a low ionization energy. They're on the left side of the periodic table. Nonmetals have a high ionization energy. So the strategy would be take a periodic table, put the word low in the lower left-hand corner, the opposite of the word low, top right-hand corner high, but we're going to exclude looking at the noble gases, which are highlighted in this pinkish red color. So ionization energy, here's the organization. Low goes on the lower left-hand corner of a periodic table, high, and then we can use the position of elements comparing them to where these two words are. And I'll show you how that works here in a moment. We have another trend which is identical to ionization energy. It's called the electronegativity trend. Electronegativity really has a different meaning. It's the ability to attract valence electrons. This is really what nonmetals do. And when they attract, they form a chemical bond. So electronegativity probably relates better to our nonmetal atoms. So again, low would be on the lower left-hand corner. High would be on the top right-hand corner, but we exclude the noble gases, highlighted once again in pink or red. So we write the word low, lower left-hand corner, high, upper right-hand corner. That'll reveal our trends or patterns. We'll get to demonstrating how that works in just a moment. We have a trend for something called electron affinity. Again, the trend is identical. It's just a different meaning. Electron affinity means there's a change in energy whenever an atom gains a valence electron, and that change in energy can be described as a low amount or a high amount. And we put the word low on the lower left-hand corner, high in the upper right-hand corner. We exclude thinking about the noble gases because they don't like to interact with their valence electrons. They already have 8. And let's put this to use in terms of using some actual information. So let's get a copy of a periodic table handy here. Let's see where we got. We got one right here. Let's clean this up a little bit. I used this a moment ago on a different video. So we'll get rid of all these crazy markings. And we'll pick any of those trends because they're identical. So the way I would go about it, if I were doing this in a classroom, I would put the word low down here. That's where our low values are for all three of these trends. I would put the word high in the opposite corner, top right. Low is a L word, lower left-hand corner. That's where it belongs. High goes to the opposite corner. I'm having trouble getting a text box here. Here we go. We're going to exclude the noble gases because they really don't behave in a way where they like to do much with valence electrons. So I'll mark that up a color. We're going to ignore those when we talk about these. And let's pick some elements. So let's say we pick lithium, oxygen, rubidium, and maybe, I don't know, how about carbon. And we want to compare these in ionization energy from in increasing order. So from lowest to highest is basically what that means. So let's mark that up. Ionization energy comparison. Ionization energy, increasing order. So I'll just put increasing there. Lowest to highest. Again, the word low is down here, right? Rubidium, right, is the lowest. It's closest to the lower left-hand corner. So we could put rubidium first, RB. Right, we start moving upward, right? As we go upward, it gets a little bit higher. Now we see that lithium is right above rubidium. And then we need to move across to compare to these other two. Well, moving across from lithium, we see carbon first. So carbon is the next highest. And the one that is furthest right, nearest the top right-hand corner, would be oxygen. That would have our highest ionization energy. So moving across the periodic table, right, it increases in ionization energy. Moving down, however, it decreases in ionization energy. And that's because that's energy needed to remove electrons. You don't need a lot of energy when the atoms are really large, because the attraction for those valence electrons is rather weak as they get larger. So let's just pick a different trend. And again, the patterns are the same. Low and high is placed in the same spot. So let's say we wanted to compare electronegativity. But this time, let's say we want a decreasing order. So that means highest to lowest, right? Highest to lowest. So let's pick a different set of elements. And we want a decreasing order. So let's use a new color. Let's maybe make a gray color. Excuse me. So we'll pick well, that's not gray, Brewer. What are we doing here? Let's go with this blue. Magnesium, phosphorus. Let's say we want bromine. And maybe we want francium. Okay. So how are we going to deal with this? Well, we're going to look at the decreasing electronegativity. The further right you go, right, the closer you are to the nonmetals. Electronegativity is this idea where we attract valence electrons, which is really what phosphorus and bromine want to do. So we know that those have higher electronegativity. They're also way far to the right. So we got francium here, which is way down here on the lower left-hand corner. That would be our lowest electronegativity. So let's say francium. Then we would approach magnesium. And now it gets a little hairy, even though phosphorus is a little bit higher than bromine. Bromine's quite a bit far to the right. The further you are to the right, the more non-metallic the behavior actually is. And that would make bromine more electronegative, higher electronegative than phosphorus. So it's a little more obvious if you have elements that are all either in the same period or the same row, meaning something like if we were to use a yellow color, right? So let's use our yellow markup tool here. Yellow, right? Potassium, calcium, gallium, arsenic. If you kind of look at what's going on here, as we move to the right, we're moving across the same row, aren't we? As we move across, we're moving toward the word high. So the lowest would be potassium, calcium, gallium, or arsenic. And that would be the lowest ionization energy. It would be the lowest electronegativity. And it would be the trend for the lowest electron affinity as well. The trends are identical. The low amounts are on the bottom or lower left. The high amounts are on the top right. And we exclude these guys here called the noble gases because they really don't like to interact with their own valence electrons. So I hope you found this lesson a little bit useful, and I wanted to try to keep it brief to give you your best chance for staying attentive. Until the next time, this is Mr. Brewer.